Hello, and welcome to the second part of this video series. Today we will be deriving expressions for the air pressure and the air temperature as a function of altitude for a decrease in the air temperature modeled by an adiabatic reversible expansion. We'll be using the basic equation of fluid statics as well as dealing with ideal gas laws. That being said, let's go ahead and get started. So let me give you a little bit better picture of this adiabatic reversible expansion idea that we're covering. So we're given this air particle at a certain height, say given height of z equals 0, this altitude, and as it increases in altitude, it increases and it expands, correct? As this z increases ultimately, and that is what we're trying to find out, how the air pressure and temperature correlate with z as z increases. And we're going to be using the generic fluid statics equation that we have over here to derive those two expressions. So let's go ahead and get started. I said over here I have the generic fluid statics equation, which simply states that the change in pressure with respect to the change in z in altitude is simply equal to the density of the fluid multiplied by the acceleration. And we can go ahead and use this further, as we know that this is in a generic sense that we're using gravity for our acceleration. And we know that as we go up, it is positive, as we go down, it is negative. So we can change this acceleration into being negative g, so that we have that the change in pressure with respect to the change in altitude is simply equal to the negative density multiplied by g. Okay? Then we can go ahead and take this one step further from our chemistry and ideal gas law basics, as we know what density is. We know that the density is simply equal to the mass divided by volume. And we can take this also another step further. We write this as we know that the mass is simply equal to the amount of moles multiplied by the molar mass divided by volume again. We can go ahead and put this back into this generic equation so that we have change in pressure with respect to altitude is simply equal to negative v over g. Right? Then we can go ahead and take this even one more step further and simplify for v. From ideal gas law again, we know PV equals nRT. I don't even know why I'm writing this down, but we know this. So then we can rewrite V simply equal nRT over P. Right? So then this can be rewritten as dP over dz simply equal to negative, and then the ends cancel out. So then we have negative P m over RTG. That is our worked out fluid statics equation that we'll be using today. So next, we know that this is an adiabatic reversible, and thanks to that we can go ahead and use the first law of thermodynamics to our advantage and use that to get our expressions. So what does the first law of thermodynamics state? It states that the change in internal energy, in this case dU, is simply equal to the heat added, or heat taken into this case, Q, minus by the work done on the system. And the system is just going to be P dV. Right? And then we can go ahead and keep on rewriting this, as we know that there is no heat being taken out of account into this first fluid expansion. So that we know that Q is 0. And then we also know that, since it's adiabatic, we know the internal energy can be rewritten as CV dt, right, as it is the critical point with respect to the temperature. And then we just add Q is 0, so we would leave that, and then we'd write P dV. And then from here, we can go ahead and simplify this by doing what we did over here, by placing P. We can replace P by RT over V, right? Plug that into here. We get CV dt is equal to negative RT over V dV. And then from here, as you guys can see, we can probably, I'm going to start to cut off, so there we go, it's a little bit better. You can see we're starting to have common denominators and factors, so we're going to put those on the same side and then start to integrate. So go ahead and divide both sides by RT, so then we have CV over R times RT dt, then is equal to, and leave this the same, and be negative dV over V. Then, like I said, we can go ahead and integrate both sides now with respect to each side. Right hand side, we're doing respect to V. This is going to be, like I said, this is going to be when we have this instance. Our initial volume is going to be when the altitude is 0, and our final volume is going to be our final altitude. So we're going to have V1 V, and the same for the temperature. The initial temperature is going to be the temperature at this case, and then the final is at this instance, whichever we're finding at. So then it's T1 and T. And then I can go ahead, or I'm going to keep that up for now. I'm going to go ahead and work this out. So left hand side CV over R is a constant, so that remains that way. So we have CV over R, and then we have 1 over T dt with respect to T over T1. So then we have the natural log, so ln of T over T1, right? And then on the right hand side, same thing but with V, so we're going to have the negative natural log of V over V1. Right? And then we can go ahead and simplify this out for what we know from basic algebra, so that we get T over T1 is equal to V1 power of CV over R. Alright, then what we can do with this is we can go ahead and work this out for values of V, right? Before I do that, actually this CV, this power here should be on the left hand side, so I'm just going to rewrite this. It should be T over T1 to the power of CV over R, not on this hand side. So then from there, we can go ahead and plug in for V. Here, what we're going to plug in is, erase this. Start up some more space. For over here, V, I'm simply going to just do what we did over here. We write this as RT over P. So if we go ahead and plug this into here, what we're going to have is RT1 over P1 all over, or sorry, it should be final. Yeah. So then this should be RT over P all over RT1 over P1. As you can see, R is common. We know this, so those cancel out, so that we end up with TP1 or T1P all over P1T. Then we go ahead and we'll bring this up here and keep working this out so that we end up with T1 CV over R is equal to T1 over T times P over P1. Right? And from here, what I'm going to do is multiply by T over T1, both sides. so that we can take this out. Then we go ahead and then we end up having T1 for CV over R plus 1 is going to be equal to P over P1. Beautiful. Okay, now we're almost there. However, there's an issue with CV over R plus 1. I don't know if you might recognize from our material and energy balances courses from the past, but from one of those videos, I discovered on how to rewrite this, as it ended up being pretty much, don't want to make too much of a mess, but in words, this becomes a CP over R, right? So then I can go ahead and rewrite this as T over T1 CP over R is equal to P over P1. And then we can go ahead and rewrite this in favors of temperature or pressure accordingly. So let's go ahead and do just that and rewrite this in favors of T, so that we can go ahead and plug this back into here, right? You see how this is connected now? So go ahead and do this over here. Make sure you guys can still see. Okay, so we have T over T1 to the power of CP over R, so we're just going to simply inverse that so that we have T1 is equal to P1 to R over CP. Then go ahead and rewrite that for simply T as T initial multiplied by that whole pressure thing. Now we can go ahead and plug this back into our initial fluid statics equation to then get our derivations for the pressure and temperature. Apologize, but let's go ahead and plug that back into there. So we had change in pressure, respect to change altitude. We ended up having this, so I'm just going to write those same things. PMG all over R, and then this is where I bring in the new temperature that we found, so denominator of Ti. Then I have to multiply this out, so actually I'm going to take this pressure out of the top, make this mg, and then I gotta remember I got a negative pressure here, so then actually I'm gonna keep the negative out for now. Okay, so we have a P, and then we have a P1 coming out of here. And the P's 1, we had one on the top, so what I'm going to do is going to have 1 minus R over CP, right? Because 1 P to the negative RCP, 1 minus the R, right? And then for this, it's just going to be R over CP, right? Okay, and then from here, we can go ahead and work this out and start integrating to simplify, right? So put this on like sides so that we have, I'm going to put this pressure over here so that we have P1 minus R over CP dP is equal to, and then here's we're going to have all our constants, RT1, P1 minus RCP. Sorry, it's the other P1 R over CP dZ. Right? And then we do what we do again. We integrate both sides. Right? And then this side we're integrating dZ, but we're only doing from as this remains constant, right? So we're only doing this. So Z1 Z, and then same with here, pressure P. Or since I switched sides, this should be a inverse, so RCP minus 1 should be inverse. And then we can go ahead and work this out, right? So for the left hand side, we're going to have p to the negative 1 times p to the power plus 1 to RCP. And then this hand side is going to remain the same. We're just going to have z minus z1 on the right hand side. So get that out, RT1, P1, RCP multiplied by z minus z1. And then, of course, this is from P to P1, or P1 to P. Okay, starting to look good. And then, or actually, this should be the inverse because we're doing the x and minus. Yeah, so this would be the derivative. So CP over R. Thinking. Yeah, because then, okay. Then we work this out so that we get CP over R multiplied by PR over CP minus P1 at that place, R over CP. And then right hand side remains the same. RT1, P1, RCP, Z minus Z1. Then we can go ahead and divide both sides by CP over R, so that over this side remains the same. We get P from RCP plus P RCP1. As you can see, PRCP1 is on this side as well, so we're going to end up taking that out. For now, multiplying by R, so this comes out, and it comes out with a CP, so negative CP G over TI, P initial, we divide by R, I'll divide by CP, so this should be the denominator, sorry. Should only have mg in the numerator, and at the bottom we have CP TI. There we go. And then from here, I said we can go ahead put like terms for the initial. So on the left hand side, all we're going to have is the initial PRCP will be equal to, and then so this is going to be, pull this out on the right hand side, so that it's going to be PRCP, and then all, it's going to be 1, and then minus this whole thing left over. The Z minus ZI. And there we have it. And then now all we have to do is divide it accordingly by RCP. That we end up with our equation for pressure to be equal to the initial pressure 1 minus mg CP Ti Z minus I to the power of CP over R. This is our derived expression for pressure. Then now we can do, well, we can go ahead and put this expression back into here to solve for our expression for temperature. Well, I might be able to squeeze it in. Just gonna make a little bit of room right here. Okay, so I'm gonna bring these two back together, plug it in to get our expression for temperature. So then we have Ti, and all we are is plugging in for initial. So if we imagine P1 and it's divided by P1, it ended up so, we can just simply take that out, simply raise everything to the power of R over CP, right? So we can do 1 minus that whole big thing, CP Ti Z minus C1. And then, so we have pressure, P1 takes out. We'd only have the temperature being at the value of R over CP, or CP over R. Those would be our, or no, there would be no CP over R. These would be our final two equations. I'm going to rewrite these a little bit better so it's seen. Okay. I said for pressure, end up getting initial multiplied by 1 minus that whole mess of things. All to the power of CP over R. Then for temperature, it's going to be the same idea. 1 minus mgCpTi Z minus C1, and then box that in. There we have it. Those are our two derivations for the pressure and temperature with respect to the increase in altitude. There you have it.